welcome to Module 25, Visualization, Grammar, and Taxonomy. Notice there's no comma here, even though I kind of said it as if there was one. Visualization, Grammar, and Taxonomy. By the end of this module, you should be able to name and use some core visual variables. This comes from someone called Bertin, and explain how they relate to a visualization grammar. You'll be able to classify charts by task. So these are comparisons, trends, distributions, and so on. And you'll be able to pick an appropriate visualization for each. You'll be able to read and critique interactive examples. I'm going to show you a library called Niveau.rocks using the language of marks, channels, and scales. You'll be able to implement two basic but honest visualizations in Python. And the keyword is honest, that respect data types and units. And you'll be able to explain to a non-expert why a visualization is or is not appropriate for a given decision. So I think I mentioned at the very beginning of this course that a major aspect of data science is trying to take a lot of data and then to derive kind of a signal from it that elucidates information, some kind of knowledge that we can convey and help us make better decisions in the world. So far, we've seen a lot of kind of tables produced in pandas that were more or less numeric with some labels associated with it. Maybe we use group by to get those intermediate tables. But more or less, we had things like this. This is actually a link to Our World in Data, which is a great resource for data analytics. In this table, this describes the natural population growth rate versus the median age in 2023. So how fast is the population growing versus like what is the median age? We talked about medians not long ago. This full table has about 18,500 rows, and you can scroll through it here. You can see there's an awful lot of it. This is an interesting table because they have numbers and they also have kind of a very small visualization of the change from 1950 to 2023. But as you scroll through this list, I mean, everything is scaled in such a way that it's really hard to tell any major differences. So Fiji, Finland, France, French Guyana, French Polynesia, Gabon, Gambia, Georgia. Well, Georgia's a bit different, but there's a lot of similarity across these rows here. And certainly, if you're only looking at the numbers, if you only have the numbers, it's really hard to tell what kind of trend is occurring. But if you take the same data and represent it as a graph, you get this visualization, which is very nice. And again, you can interact with it yourself. So this graph shows several things. Each of the continents are colored in their own color, so you can kind of see very quickly at a glance trends across different continents. So here in purple, you can see African countries. They tend to have a very low median age. They're off to the left, and they have a high annual rate of population increase. And then if you look at places like Europe, the median age is older, and the annual rate of population increase is smaller. North America is kind of stretched out a little bit. Asia, Oceania. So it's really kind of Europe dragging things down a little bit. You can also see some, the circles here represent, I think this is the size of the countries. So India is a big country, China is a big country, and so on. So you can see like the effect of these relationships in median age and annual rate of natural population increase. At a glance, how is this affecting big countries and small countries? There's an awful lot of fairly big countries by population in Africa, and they're growing quickly. You can see some outliers here. So the Vatican, for example, is an outlier in that it's very old in terms of its median age, and its annual rate of natural population increase is also pretty low. There might be reasons for that outside of the mere relationship between median age and annual rate of natural population increase. There's some domain expertise to tell you why this point is where it is. But generally, unlike the table of numbers you saw a moment ago, the overall trend is pretty clear. There's a very tight line that kind of inversely relates these two variables. The older a country is in terms of median age, the lower the annual rate of natural population increase is. And this kind of makes sense to us, obviously. But it's nice to kind of visualize things. And you can scroll back and forth to see how things change over time as well. So this is basically just highlighting the importance of a good visualization. So this is a little thought experiment. Imagine this table, it goes back to say 1960. Imagine you're only looking at, on the order of 10 or so countries. And ask yourself, how easy would it be to see at a glance which country gained the most if all you have is yearly entries. And how easy would it be to observe that same thing if you had a visualization like we saw in the chart above? Some questions to consider and mark down in your journal. When did the chart feel clearly better than the table? On the other hand, when is the table necessary? You know, as a spoiler, I guess, maybe you need exact values. Maybe you need some kind of better documentation that the chart doesn't provide. Maybe you need to debug problems. Like there didn't seem to be much of a problem in that chart, but maybe there's a problem that you need to debug by going back to the raw data. And then finally, which visual variables, which we haven't really described yet, but you've kind of seen color, shape, size, and so on, which visual variables are doing most of the heavy lifting in the chart to tell you, you know, the important information that we're trying to glean from the data. So generally we know the visualization elicits structure quickly. We saw that linear relationship extremely quickly in a way that we just couldn't from the table. But, you know, sometimes we might still need the raw underlying data. I want to just take a quick detour to Anscomb's quartet, or Anscombe, I guess. You can read about it in this document. So these are 4 different data sets, data set 1, 2, 3, and 4. Each of them have the same means, standard deviations, correlations, and even simple linear regressions, which we're going to talk about in a future module. It's basically just a linear fit through the data. We have all of these high-level like statistical metrics that basically say data sets 1, 2, 3, and 4 are identical. Like, again, means, correlations, everything is totally the same. Here's just a data frame, with the X's and Y's. Looking at these numbers, I don't see any particular pattern. You know, I just see a lot of samey-looking numbers. So if the numbers look kind of similar in this table, and I'm told that the statistics are all the same, then I'm going to guess that these data sets are very similar in some way. But of course, that's not the way things are. If we were to graph that data, you were going to see data sets 1 through 4 have very different patterns, right? Data set 1 has sort of a realistic pattern of the type we've kind of seen. There's more or less a linear relationship, but there's an awful lot of noise. Data set 2 has a very clear nonlinear pattern, this kind of bending arc. There doesn't seem to be very much noise on this bending arc, but it's clearly a very different data set than data set 1. Data set 3 is clearly linear most of the time, with almost no noise, almost no jitter, so to speak. But we have this one outlier up here at the top. And then finally, data set 4, there's also a clear linear relationship. That linear relationship is mostly just like everything is clustered around this single value of x. And again, there's this outlier with a high value of x over on the right. You can satisfy yourself by going back here and computing mean, standard deviation, correlation, and so on these data. And you'll see that, and also the regressions, these lines that I've plotted through these data points. And the metrics say these data sets are the same, but clearly they're not, right? So just something to consider. There's always more to the story than that first meets the eye. This is related to this other work from 2017 called the Datasaurus example. And there's a link you can follow that kind of where I get this image. Every frame in this animation will have approximately also the same means of both x and y, the same standard deviations of both, the same correlations. You can see that happening here live. There's some, as you get to the smaller significant digits, there's a lot of changes going on, but to the two most significant digits, there's no change between the star and these lines and these vertical lines, the x, the horizontal lines, the two, and so on. Everything, even the dinosaur image, which is coming up there, all have the same values, which ought to be a bit surprising to some people. But again, this just reemphasizes the fact that we have statistics. We have even tables that are just the raw representations. But on the one hand, the raw representations will be, too detailed for our squishy human brains to kind of get the high-level patterns at a glance. The high-level patterns at a glance, which we're trying to get out of the statistics, like means and standard deviations, also are going to be uninformative. So a visualization helps us and how humans process information very quickly get a high-level sense of what's actually going on in a way that the raw data and the statistics just don't provide. I I want to, speaking of visualization, which is the topic of this module, go through a little bit of history to, again, reemphasize the importance of this subarea of science. So cholera is an infection of the small intestine. It's very deadly. In around 1854, a cholera outbreak shook London, England, not London, Ontario. And around that time, again, coming back to a topic that was in our very first module, I believe, people who didn't have access to the scientific method cognitively kind of thought there was this vague thing called miasma that spread this disease. But John Snow, no relation to the character from the Ice and Fire books, established the field of epidemiology and plotted the homes of the infected patients. He took a map of London, England, and I'll zoom in a bit. Each of these dots represent like where these instances of diagnosis of having cholera were measured. And if you zoom out, you can see there's a kind of a big cluster around here. If you zoom in, there's a very strong cluster right here on Broad Street. Where this X is marked is a water pump. And indeed, people from this area were just walking to this water pump, getting their water, and because they were all using the same pump, they were spreading the disease. There are a couple of outliers that exist, all over the place, but that's because people were just carrying water great distances. But regardless, this visualization identified the kind of the epicenter of the problem. It was a water pump. Removing the handle basically ended the outbreak, and it was a fantastic victory of visualization in data science to a large extent in public health. Menard produced this graph that you can see on Napoleon's 1812 Russian campaign. And this graph combines a couple of things. Troop size is the width of the graph, the tannish region over here. The location from west to east as the troops marched from France towards Moscow. And the direction, the temperature, which is shown, I believe, at the bottom here. Tableau graphique de la température en degrés. So this is the temperature down here, correlated with location and time, right? So like there's a left to right movement as the troops march forward over the course of what looks like several months. And you can very quickly at a glance see, that there's a great amount of dissension, or like people they started off strong, and gradually the troops winnowed away and diminished by the time they got to Moscow, resulting in, of course, one of Napoleon's most tragic defeats. Well, tragic for him. This is actually an example of the Sankey graph. We're probably going to see examples of this a bit later. You've probably seen graphs of this type where you have kind of a left to right motion where widths of the visualization are meant to indicate a change of some quantity over time. And then finally, this for an historical context, we talked about disease, we talked about war, now disease and war. Florence Nightingale was an accomplished nurse and statistician, and she was an early innovator. She was so innovative that she even invented the word innovator, which I'll try to fix. So she basically helped design new kinds of plots to analyze data. And she plotted casualties in the Crimean War, one of several. This one also occurred in the mid-1800s, coincidentally. What these kind of radial-looking graphs indicate is the different kinds of casualties, like death and otherwise, graphed over time. So you have July, August, September being different wedges of this graph. And what she did was she just kind of colored this graph by the kind of nominal nature of the casualty. So black is death, red is wounds, so people were still bedridden, and then blue is disease, right? And if all you had was just overall casualty counts, you would have no real indication of what is the source of the casualty. But right here, you can see very clearly that the overwhelming amount of casualty is caused by disease. There are problems with this kind of radial graph. If you're measuring amounts along one of these lines, like one of these edges of this radial graph, you can kind of mark off, where the proportions of wounds, death, and disease. But as you rotate this wedge around, you're going to sweep out an ever-larging area for the regions that are further away from the center. And this can kind of visually overemphasize the whatever region you have on the outer edge, right? If Florence Nightingale had put blue towards the center, it still would have probably indicated, a heavy influence of disease, but the blue region would have swept out a smaller area than it would have if it was placed on the outer edge like it is here. So just a thing to flag. We're going to talk about pitfalls in the next module, but I just wanted to mention that. But again, just keeping with this theme, this early form of data visualization, again from the mid-19th century, was extremely innovative, and it led, in this case, to inquiries on sanitation. And thereafter, after this intervention caused by this visualization, there were significant improvements in barracks and hospitals and overall casualty rates. Another great victory, just like John Snow's, that we can observe through high quality visualization. So again, let's go to our conceptual scaffold. We want to have a mental model for thinking about visualization design, and we're going to treat visualization kind of like a sentence. So, a grammar is how we put parts of speech or words together. We want to think of a visualization as a syntactic structure over little elements, and we want to think about those individual elements as well. How a sentence, a grammatical sentence, fits together, and how a visualization sentence fits together. Well, we need to understand what is the purpose. So, like, what is the task? Who is the audience? What kind of decision we're making? This is related kind of like to the pragmatics of speech. Like, why are we producing this visualization? We need the content. We need the actual words and semantics of the sentence. So, what data do we have? What attributes? What kinds of abstractions are going to be present? And then we need the grammar. The grammar is the syntax, the rules that let us draw everything together. Are we going to use marks, channels? What kind of flexibility do we have with the layout? This is related to like the grammar of a language. So these questions come from Munzer. I should add a citation here just for those who are interested. But we have the why, the what, and the how. So let's go into each of these. Oh, here's the reference. So I got ahead of myself. There's two of them actually. The why. So a widely used definition in visualization research is computer-based visualization systems provide visual representations of data sets designed to help people carry out tasks more effectively. More or less how we've been defining things so far. The task is the reason someone is looking at the graphic at all. This could be someone you work with. They get a report, they get a Jupyter notebook, they get a visualization, and we want them to be able to make some informed decision based on it. They may want to compare groups. They may want to find outliers. They may want to understand the trend, like we saw with the Our World in Data graph. We might want to, check whether a model that produced the data is reasonable. Or we might want to communicate some result to a non-technical audience. Maybe you and I, we have a deep technical knowledge of how the model is constructed, but we need to demonstrate what it's learning to an audience of people who don't understand the technical details. So the evaluation-focused writing of visualization, so taking a visualization and then evaluating it to see whether or not it's a high-quality, good visualization or not. It emphasizes that we can't really judge a graphic using only a single metric. You can't just look at a visualization and use one measure of clarity, for example. It's a multivariate question with lots of interaction between the variables. But generally, we want to ask overall, holistically, does this visualization help the audience perform their task accurately, quickly, and confidently, or not? And answering this question is going to be the work of several subcomponents. So let's. This is just a very simple example. This is a scatter plot, like we've seen several times already in this module. We have the data. We might plot this dashed regression that kind of passes through these dots as closely as possible. And this tells us things like, what is the overall trend? Is it increasing? Is it decreasing? Is it more or less like a straight line? Or is it a nonlinear curve? Or is it something different? Can we use this visualization to find outliers? Like, is this dot over here at x equals approximately 1.7 or so, and y equals 20? Is that an outlier, or is that like a reasonable data point for this trend we're observing? This is the kind of thing we can observe, or those are the kinds of questions we can ask on a visualization such as this. So that's the why question. The what question is overall data set types. So we want to understand the structure of the data we're visualizing. And again, continuing to follow like Munzer's work, we want to distinguish different data set types from attributes. So what is the overall structure? And we want to separate that idea from the individual attributes, or what we called columns, or sometimes we call them variables in past modules. So common data set types in this course might be tables, the rows are items, the columns are attributes, like we've seen many times with pandas and the tidy table conception. We might also see networks. Those are going to come up later in this course. So nodes, links, relationships. This is something like social networks or citation graphs between academic papers. And then you might have spatial or fields or heat maps, so temperature over a map, pixel intensities of an image, areas that a model might be focusing on to make a decision in explainable AI. Those are all different data set types holistically. So the type of data set you're dealing with will strongly constrain the kinds of plots that you can make, right? So a table with rows and elements as columns, might be amenable to scatter plots, bar charts, line graphs, even heat maps, but basically a lot of the kinds of visualizations we've actually been seeing throughout this course so far. Whereas networks might lend themselves to node link diagrams or maybe a matrix that shows adjacency, like so relationships between elements. And then spatial or fields might have things like choropleths, which we're not going to talk about too much, or contour plots or raster images. So again, high level, the holistic type of data set you have will kind of inform what kind of visualization might actually be possible in the first case. So this is just like another tiny tidy table with student ID and then some information we care about. Here, rows are students, columns are attributes, easy peasy. This kind of table might not lend itself to these kinds of visualizations. So here we have the network sort of visualization we talked about a moment ago. Each of these nodes might represent an element, and the edges between them, whether they're colored or not, the intensity, the thickness of these edges might convey some information. On the right, we have this field. It's basically a pixel. Every location has a value. It's like a heat map. This could be like an indication of regions of the country where a disease might be breaking out, or average income per household or something of that nature. Something that has a two-dimensional quality to it. Within an individual table, there are different attribute types. This supports different visualization encodings. So this goes way back to the way we've even talked about data in the first case. We talked about categorical data, so like nominal. So this is unordered labels, species, the major you're part of, the country you live in. We talked about ordered or data or ordinal data. There's categories. There's still labels. There's some meaningful order, but maybe the spacing isn't quite equivalent. So like Likert scales or grade bands, A plus is better than A, but is the difference between A plus and A the same as the difference between a C plus and a C? Maybe, maybe not. And then we have quantitative. These are good old-fashioned numerical values like integers and floating points. The differences are meaningful. You can take ratios, you can take some statistics, averages, so things like age, height, income, probability, a lot of the kind. This is a data type we've seen a lot of. And the kind of data of this type, so the actual attribute type you're dealing with, will also have a heavy influence on how you visualize the data in a image. We might care about key versus value attributes. So whether one of these variables is something we're measuring, like someone's age or height, or if it's a key to the value, like an identifier. This can have a major distinction. I don't really care necessarily about the difference between student ID 101 and 103. The fact that the difference is 2 doesn't really mean anything. But that ID can be thought of as a label, which might just identify different nodes in a graph or different regions in a visualization, etc. If there are derived attributes, so residuals, percentages, z-scores, other kinds of ratios, averages, these will also, like in these examples, they all tend to be quantitative and numeric, real valued, continuous variables. So how we would convey that on a graph would, be on a scale as opposed to isolated in different like nominal buckets, if that makes sense. Unless we go through the exercise of binning them like we talked about in a previous module. So just to hammer this home even further, we have the same underlying concept. We have some notion of level. So each of these graphs kind of represent levels, but the attribute types are different, and this leads to different appropriate plots. So when we have categorical data, so we still have levels like an A grade, a B grade, C, or D. Here they're described as if they're nominal categories or labels. Those tend to be what we put on the x-axis or the independent axis of a graph that we'd use like a bar graph like this. Sometimes people use data which is, or visualization which is like as if it's ordinal. So they'd kind of order the labels here on the bottom, and then they'd still use a bar graph, and that's usually kind of fine. But you have to be careful. We'll talk about ways that can go wrong a bit later. We have ordinal, like low, median, and high, indicated here as just dots. And then we have overall quantitative measured data. So we have like, again, bins. We've quantized the data into these sort of bins over here from -2 to 2 or so. This is an example where we might use a histogram. So here, like technically, it might look like this graph on the right is just a highly squished and slightly more detailed version of a bar graph like the one we saw on the left, but that's not really the case. Obviously, we're drawing these big blue rectangles, that extend upwards as we go from left to right. But in the first case, you can swap around A, B, C, and D and not lose any information in the visualization. Whereas I cannot take this this actual linear scale here and then just take these rectangles and just shuffle them around, because doing so would break the underlying attribute, which is the x-axis for this graph. So that was the why and what, but now we have to answer the how layer, how we can actually turn data into pixels. So this follows the semiology of graphics. This is relatively old, but other more recent work has followed up on it. This kind of describes the low-level words of a visualization. So I'll just go through them now quickly. The marks are the basic geometric objects that appear in the plot. So these are points, lines, areas. They could be bars or polygons. They could be text and labels. They could be volumes in 3 dimensions. There are channels. These are also called visual variables. These are properties of marks that we can change. So for a point, for example, we can change its position in XY or XYZ. We can change its size. We can change its shape. So a point can be represented as a square or a star or a triangle. We can change its color in various ways. So the difference between hue, value, and saturation, we won't go too much into in this class, but you probably know the difference between some of these aspects of color. Their orientation can matter. So maybe each of these points, or a line may be a better mark to mention for this particular channel, but the orientation of a line can be very informative. If you're plotting a line that's more or less flat and horizontal, that might mean that there's no major change in the y-axis, whatever that variable is, as you change the x-axis. But if if the slope is very high, if the line is more upwards, more vertical, that has a different meaning in terms of the interpretation of the data. You might apply textures to regions. You might have like certain patterns that indicate that this region is different than that region. And then it goes on. So we're going to see some examples here, but you might come up with other examples on your own of different ways that you can encode information using these channels. This could be like motion if you're doing something like a video or an animation. You might have some blurring, you might have transparencies. Does the transparency convey any information, or does it just help the viewer sort of focus on what they're looking at? That's another question for the next module. So when we're thinking of the grammar, the how do we convey information, we just want to understand which attributes map to which channels on which marks. So we have attributes like the variables in the original data. We want to represent those individual attributes, those columns of data, as marks, for example. Are they points, lines, areas? Once we've made that decision, how can we change the channels or the visual variables so that we actually convey the information we're trying to convey in the first case? Here's just a visualization of some of these concepts. Our marks can be points, lines, or areas, and then the channels can be position. So here I'm changing on all these examples, I'm changing the position as I go from left to right, but here I'm also changing the position from top to bottom. I can change the size, or I can change the color, right? So each of these sort of, like, as you probably grasp intuitively, convey different amounts of information, right? So the size of a point might indicate the degree of something. You can go back to the Our World in Data figure before, where we looked at like birth rates versus median age, and the size of the circles conveyed information, which is the overall population of those countries already. We'll see other examples of this soon enough. And the color can convey information. Again, going back to that graph, the color of the circles represented the continent on which the country is found, right? So you can see kind of at a glance, is there a big difference between one continent and the other based on the differences in color? Again, here is the same data, but different channels. So we have categorical data on the x-axis from A to E, and then we have the values here, right? So the bar graph, the position and length, make it easy to compare values. You can see at a glance that A is 5 times more, whatever the value is, than E. It's also a bit more than twice as much as B. So you can see that at a glance looking at this graph. A is the winner if value is a good thing, or the loser if value is a bad thing. On the right, we have something that may look a bit fancier. So sometimes when people do visualizations, they think it means the same thing as aesthetics, or some kind of artistic quality. And that's, maybe sometimes partially true. We like graphs to be compelling and pretty to look at. But the form, the aesthetics should be secondary to the function, which is to inform. So inform is more important than form. So here's the same information, but I've encoded these values here as just the size and color of these dots, and right now it's really hard to tell much of anything about the relationship between these dots here, or these categories A, B, C, D, and E. Okay, so the main point here is that always think that you're trying to convey something. At some point, you're going to make it pretty. Maybe that's the last thing you want to do, but not at the expense of losing information, at the expense of losing the core signal. So McKinley has a classic paper on automated chart design, and this introduces 2 key criteria: expressiveness and effectiveness. So in expressiveness, the visualization will show all of the information in the data, and only that information. So if we have categorical data, like just labels, we're going to be very careful not to imply that there's some kind of order, right? So we won't say A is very light and B is somewhat darker and C is somewhat darker still. A, B, and C, they're categories, they're not arranged, they're not ordinal in this example. So we shouldn't have any kind of a visual variable or channel that might kind of imply that there is an order, okay? If there's no order, we should not convey it. Effectiveness is the second criterion, which is that the chosen encodings should exploit human perception, so the most important information is the easiest to see. This can rely a lot on kind of cognitive psychology. So this is one of the very many instances where computer scientists ought to step outside of computer science and learn a little bit what other disciplines are doing, or collaborate with people from different disciplines. So often those who work in human-computer interaction might interact with those who work in information and cognitive psychology and other types of sciences outside of CS. Humans have biases. We're going to see a lot of them again in the next module. A lot of different strengths that we have visually, and it's important to be aware of those when we're building our visualizations. So a consequence of having high expressiveness and high effectiveness is that we have these sorts of rules. For quantitative or measurable attributes, we prefer channels like position on a common scale, length, sometimes angle, to some extent, can be helpful. We'll actually mention in the next module that sometimes small differences in angle like humans might have a little bit of trouble distinguishing between them. If you have an ordinal, then again, position is still a useful channel for you. Now, value or lightness might play a role. So now if you're talking about grades A+, A minus, B+, B, B minus, and so on, then suddenly there's an inherent scale or gradient. So now you can apply a gradient or scale to representing those elements, A+, A, and so on. Size might work well as well. And then for categorical attributes like labels, color, hue, a shape. So you could say this point is one label by representing it as a square. This other label, this other data point is another label and represent that as a circle. So change the shapes. Occasionally distinct regions can be appropriate, but being expressive, being effective means relying on human cognition, human biases, and then that'll tell us which visual variable or channel we should use for conveying the underlying data. I want to take a brief moment to talk a little bit about how to actually implement these things. You might have noticed on the course website there's a couple of regions where I use a library called Nevo. I just, I'm linking here to the actual page. You can check it out yourself. There's a lot of visualizations here. I use Bump, for example. I also use a tree graph, which is down here. But there's a ton of different visualizations, only some of which we'll get a chance to talk about in the next couple of modules, just because of time. But I really advise you to play around with this and become familiar with some of the differences here. So this is a simple bar graph. We have categories broken down as separated regions on the independent axis. And then we have things that we're measuring, which is amounts of food and like overall in these different countries consumed, presumably. This is all fake data. And then we have by color, we also further differentiate between the labeled categories. So there's no order between donut, fries, kebab, and sandwich. These are all labels. So different colors are reasonable ways of differentiating these different values of food. So the mark in this case would be a rectangle or like a region. The channels are position, which indicates category, height, which indicates value, the numerical value. The hue, the color here, further represents groups. And this is useful for comparisons across categories. So now you can see very quickly that country AL consumes more food than country AD, for example, at a glance. Then we have line graphs. So again, here, this one is something I might disagree with a little bit. So here we have the different countries, again, are represented by different colors. And you can see that in this line graph. Here, I think that the problem is this is actually an error. So I think this is a problem. This is like a negative case or what I call an anti-example. Now we're drawing connections between these points, right? So there's a line from plane to helicopter to boat to train, indicated by these lines between points over here. But these transportations methods, is there an order between them, right? Does helicopter follow plane? Does bicycle follow motorcycle? I'm not exactly sure. I don't think so. Connecting them in this way kind of indicates that there's relationships that are consistent that might not actually be true. This is a bit of an example of like an anti-example. So usually you'd expect the channel X to represent something like time. The Y position is value. Here, Y position is value, all good. The different nominal categories being countries or different colors, all good. But now the X-axis is still named labels, they're nominals, but they're presented in an ordered way as if they're an ordinal or a continuous variable, or if they're a discrete variable, and none of that is true. So a bit of an anti-example there. We have scatter plots, which represent sort of relationships. So here we have size versus weight of these different groups of objects. The different instances of these different objects are colored to indicate what group they belong to. The channels, the X position, the Y position, these indicate continuous variables. We could change the size like we saw earlier with countries by population. So we know what scatter plots are. And then heat maps. This is a bit more squished than I'd like, but we're going to see other heat maps later that are less squished. Here we usually have some kind of either two variables that are nominal. They don't have to be nominal, but in this case they are. So countries versus transportation methods are the rows and columns of a heat map. And then you can still put in the raw numbers into this table, like you'd see in a regular table, but you just color it or you change the intensity of every element to sort of indicate at a glance the extent of something. Again, it's kind of hard to see here, but you can see there's like negative value to positive value, which is represented by the redness to the blueness scale. So a heat map can be good for representing sort of like relationships that can be put into a matrix in some kind. If there's any kind of correlations, like a correlation matrix between variables, that's a good use of a heat map. So correlation matrices often are on ordinals or discrete or continuous scales. So you might see a heat map in which like the x-axis and the y-axis are actual like numbers, like real valued numbers. And then a confusion matrix, which we're probably going to see in the section on machine learning. The rows and columns are nominal categories, but we can still represent them in a table, and then therefore we can color the elements of this table in a way that represents the value of those elements. And then finally, Sankey. This is very similar to the graph we saw of Napoleon's ill-fated trip to the east. There's sort of a left-right continuity here. We have marks here, which are the marks we're using are nodes, these kind of regions, and the bands between them. The channels are the width of these bands. The width indicates like the flow magnitude, how much of Marcel goes to Raoul and versus John or Jane. The colors represent groups. So Raoul is orange, Marcel is red. There's nothing much going on here. It goes from red to orange. In some situations, you've probably seen Sankey graphs applied to the quarterly earnings reports for large companies, where green is good and represents positive cash flow, and red is negative and represents negative cash flow. These kinds of graphs are kind of a one way to answer like where did it go questions. You might see like a lot of income coming to a particular company, but then a lot of that income is therefore thereafter spent on things. So all of this money you raked in ends up going to your employees, hopefully, if you have any, or taxes. Hopefully, you're paying your taxes, and so on and so on. So you can kind of just see at a glance how the flow of some quantity, moves through different channels over time. So just kind of wrapping up this little topic here, Wilkinson's grammar of graphics proposes that every chart can be described in terms of a small set of components. So again, for those curious, you can check out this reference. And many modern libraries in Python, linked here, check them out, build either directly or indirectly on Wilkinson's grammar. The key components are like data, obviously. You have one or more data sets. You have aesthetics or mapping. So aesthetics, again, is not necessarily something artistic at this point. It doesn't necessarily, relate to like your style. But it still refers to what we were calling channels before. So which attribute maps to which channel, X, Y, color, size, and so on. So aesthetics isn't exactly the right word, but we're just going by convention. We still have geometric objects. We still have mark types, points, bars, lines, polygons, text. We haven't really changed any kind of conception of how we're going to be doing visualizations. The components also include statistical transformations, so any kind of aggregations or binnings or smoothings, they need to be explicit. Scales and guides, axes, legends, color bars, and so on. Coordinate systems, are we using a Cartesian, map, or are we using something with polar coordinates? So Florence Nightingale's map of the Crimean War showing casualties might be an example of a polar map, something that is in terms of radians, not necessarily XY positions. Maybe a map, maybe you're actually looking at a map of a country or a province, and then you're kind of doing some kind of heat mapping over it. That's a different form of coordinate system. And then faceting. So faceting refers to how to split data into small multiples or panels, and we'll see some examples of that later. Generally, the workflow is you start with data, you do some transformations, like the aggregations, binnings, and smoothings. You map the result to the channels. We call this mappings here. We call this channels before, same idea. This will also give you your marks and layouts. And then afterwards, after you've produced all of this, you ensure that all of your axes are labeled. Any kind of legends you need to have exist also. Just to highlight here, this legend on the right is not exactly necessary because we have all the information in the graph already. But here, the legend is necessary. If we don't have this indication of what color goes with what country, looking at just this line graph would be pretty uninformative because I wouldn't know that turquoise has anything to do with Norway, for example. So again, thinking in terms of like visualizations as a grammar, we have kind of small components that we can structure together in consistent ways that make sense. This will help us reason systematically about different possible designs we can take. And it's not about memorizing recipes. It's not like kind of going through the motions and jumping through the hoops and like giving a particular table, you have to do this kind of visualization. We still have an awful lot of flexibility, which is fantastic, and it'll help us explore things and consider which visualization is the closest representation of the truth we can find. But it's not rigid, but we still need kind of a structure in which we can think about the kinds of mappings we might produce carefully. So some tasks, if you're going from questions to these low-level actions, we're going to jump back to the why layer. We need to be a bit more specific about the kinds of tasks we can undertake. So this goes to Amar, Egan, and Stasko, or the Egans. Is not Egan, as nothing to do with the television show Severance. Anyway, they propose this widely used set of low-level analysis tasks for information visualization. I'm not going to go through all of these right now, but this include things like, well, I need to retrieve a value, or I need to find some extremum, or I want to be able to find clusters in my data. Like if there's some kind of pattern that exists in the form of clusters, I want to be able to quickly obtain that. So all of these low-level analysis tasks are pretty general, right? It doesn't refer anywhere here to health or traffic flow or finances of a city or the efficiency of a banking system or of the ports or something like that. But you can apply each of these low-level analysis tasks to any of those domains. Okay, so a CEO of a company or a doctor in a hospital might need to determine the range of something. The underlying task is the same in both cases. It's just that they're dealing with different data and different units, different possible actions they can take. But again, the analysis types they can make are the same. So when you're looking at a visualization, and we're going to see a lot of mostly bad visualizations in the next module, you can ask which of these low-level tasks should be easy, and does the encoding make them easy? Okay, so if a particular data set, it should be easy to tell which is the smallest value, which is the biggest value, what are the mins and maxes? Like, is that even easy in the first case? And have I encoded the information in a way to make this easy? Okay, if I have like a 100 by 100 table of just a bunch of numbers, and I have to find the minimum and maximum in that particular encoding, that particular channel, I'm going to have a hard time finding the min and max. Whereas if I sort everything and demonstrate it on any of the visualizations we've seen where there's like an inherent scale, like an x-axis that changes over a continuous variable, I can very easily see the min and max within less than a second. Okay, so again, what is the task I'm trying to do? Should it be easy? And how does the encoding choices, that is to say, what channels can I take to make that low-level task easy or hard? So again, we can evaluate a visualization within the scaffold that we've put together. We can think of the why question first. This is always the most important thing. Again, we're not just doing data science for its own sake, although it's a lot of fun. We're doing data science because we want to help people make meaningful, high-quality, correct decisions in the world. So who is it for? Whom is it for, I should say? What questions or decisions are they working on? What low-level tasks, i.e. these things, are going to be most important to them? And maybe also, like, what are the consequences of having incorrect interpretations of the data? Next, you can say the what. This is the data and the abstraction. Are we showing the right subsets of the data? We don't have to show everything. Are we like breaking things down appropriately? Are we coming up with the appropriate abstractions? So the aggregations, means, and like normalizations, for example. Are the attribute types respected throughout? Like knowing that I'm dealing with categorical data, am I suddenly switching to a visualization that kind of indicates that it might be on a continuum or not? So are we doing the what question properly? And then the how. Are the marks and channels expressive, and are they effective? Like, are they, like, back to the expressive versus effective question here of McKinley. So, I mean, this isn't the most, this is a relatively important thing to get straight. What does expressivity mean, and what does effectiveness mean from within visualization? So are the marks and channels chosen effective and expressive for these attributes and for the underlying tasks and for the person making these decisions? Are all the scales, axes, legends, and labels clear and readable? Again, we're going to see anti-examples in the next module. And is the important structure visible without a lot of clutter? again, going back to the earliest visualization from our world in data of population increase related to median age, it was very easy to see a very strong relationship between those two variables visually without a lot of extra noise that distracted from that core bit of information that we're trying to obtain. This relatively recent paper from Tayo, but others have also shown the same thing, talk about evaluating visualization, so judging their quality. And Tayo and others also show that it's multidimensional. It's not a single thing. You can't just say like it's a good thing or a bad thing. It's a bit more complicated than that. It's an interaction between a lot of different questions and a lot of different variables, and the variables kind of interact in a bunch of different ways. So this is just to emphasize that doing high quality visualization is not paint by numbers. It's not like just a series of steps, like a recipe you can go through. It involves a lot of interpretation and thinking. But there are ways that we can structure our thinking about this particular activity. Very briefly, mathematically, we can think of visualizations as a function. So think of like going from data to a picture as this function g. It'll take a row of data and will return a mark that we're going to put into the graph, right? So a row of input can be country, Canada, income is 46,000 Canadian dollars. The life expectancy is 82 years. We could put, we could represent this, like the function could take this input and output a circle at point x, y. X might be 46,000, y might be 82. And the size and the color might indicate whatever other information I have here. The color might just represent Canada through the color red, for example. So visualization can be thought, like when it's actually implemented, as a pipeline that turns units and labels into positions, lengths, and colors. This is not a contradiction of what I just said a moment ago. So when you actually have a visualization, at that point you have this function g that completely unambiguously takes the data and transforms it into the visualization, and that's a one strict pipeline. But other possible functions exist, g prime, f prime, whatever other functions you want to call them, that have different mappings of the same data to different visualizations. Each one of them is a pipeline, but you still have a bunch of possible functions available to you. And part of doing visualization is finding a small subset of functions that are optimum in some way. So if you have data being a big row here, like x1 to xd, you have d elements here, then the function g produces a mark type, position, color, size, and other channels. So we're going to see a penguin scatter plot. This can be like the function g could output a point. A flipper length x will be our the flipper length of the data, x, we'll find the flipper length somewhere in x1 to xd, and that will be our x-axis point. Body mass will be one of these x sub 1 to x sub d, and that'll be our y-axis point. The color of the point will be the species of those available, and the size will just be fixed to 5. So we're going to see this in a second. But this is like a pipeline. This is a mapping that says given any type of data from a particular data set, this is the exact outputs that I want to see to generate the visualization. And here is where we're actually going to use this function. So you are going to be a field biologist now, and you're going to be weighing some penguins. Okay, so we're going to have flipper lengths, and we want to know, given a flipper length, can we guess a body mass accurately to within about 300 grams? If we, and this again, but back to the ethics of it, if we underestimate the body mass and we want to try to sedate these penguins for further study, again, we're field biologists. If we underestimate their mass, we might give a unsafe sedative dose. And if we overestimate, then this might be safer but wasteful. I think this is actually the reverse, right? So if we overestimate their body mass, if we assume they're very large, this is penguin, then we might give them a sedative that is bigger, and in that case it would be an unsafe sedative dose. Whereas if we underestimate their weight, the penguin weighs this much, we assume they weigh a little bit less, we'd give a smaller amount, this would be safer, but it would be wasteful. So I think I actually inverted these two rows. I'm going to make a note and just update this before I update the slides. Regardless, this is a tiny sample inspired by the Palmer penguins data set. You can read about it at this site. There's a library called Palmer Penguins, and there's a function called load penguins, and this just loads the data, and you get something, the head of which looks like this. You have species, islands where they occur, bill length, bill depth, flipper length, body mass, the sex, and the year of all these penguins. And here's the graph, here's the code to graph it. Flipper length is a continuous variable, body mass is a continuous variable. We know that we can take these two variables and we can convert them to the two axes of a scatter plot. And because we have nominal categories which represent the species, we can change the color of the marks. Blue is Adelie, green is Gentoo. Gentoo is also a Linux distribution for what it's worth. And then very quickly you can see several things here. You can see heavier penguins, ones that are higher up here on the y-axis, tend to have longer flippers on average. They're also towards the right of the graph. There's more or less a linear trend, of going from the lower left to the upper right. So that's a bit of information we get almost immediately from this graph that we did not get from this table. And we also see that there's differences in species. So Gentoos are the biggest and have the longest flipper length. Now, there's a little bit of, if we were to remove this, actually this is a bit of exercise for you. I would take the graph, I would graph just the Adelie and chinstrap penguins. What's left over here seems to be much more of a blurry overlapping area of the blue dots and the orange dots. And I would suspect that if you were to zoom in on this area, the overall distribution of these points would be more like a cloud and less like a straight line. So is it the case that this apparent relationship between flipper length and body mass is pulled and stretched and dominated by the presence of these Gentoo penguins? Maybe this trend between these two variables does not exist if we're looking at just Adelie or just chinstrap penguins or their combination. So this is just an example of an idea that we'll keep on coming back to, and again, especially in the next module, which is like we have a visualization and we think we're finished. It's a somewhat pretty looking graph, but does this actually tell the whole story? Does it convey information at a glance? Well, it seems to, but is that information correct or not? We don't know yet. We have to keep on being curious and keep on digging. That's a bit of a surprising, I didn't know that I was going to mention this here, but looking at the graph, it seems like something kind of funky is going on. So here's another little example. This is called a tiny gapminder. We're part of a global health NGO, and we want to prioritize where to invest vaccination funding. So which countries might combine low income, low life expectancy, and large populations? And this will help us to kind of make the decision that we want to achieve. So now we're going to build a mini fictional version of the gapminder health versus income chart. Here's how we do it. This is super small, but this is only for the purposes of explanation. Here's our raw data. Hard to see at a glance any kind of trend here, but we can just take this table, convert it to a little graph here. As you can see, it's another scatter plot with these channels or parameters. So again, a moment ago we talked about channels and different mappings that we can go between the data and the visualization. Well, here's the raw data. We have the region is a column of every row. We have a mapping that maps the possible labels to possible colors, and then we set the color of each of our dots to be the color indicated. So the mappings are all kind of provided in Python in matplotlib in this way. And now we have a little bit more information here, not too much more, but we see, well, Asia sort of dominates in terms of population size. The income per capita is sort of medium. The life expectancy at birth years is sort of median also. If we go towards the left, this goes back to the question of whether we could answer high-level questions easily. What is the region with the lowest income per capita and relatively low life expectancy at birth? We have a couple of countries here from Africa that seem to be dominating this lower left-hand side of the graph. I should have labeled these circles with the actual country names, but this one towards the bottom seems to have the lowest life expectancy at birth and fairly low income per capita. Maybe this is a region we want to focus on. This doesn't necessarily prove by itself which interventions will be the best. Like, I'm literally just talking off the top of my head now in a way that might sound plausible, but you have to always be careful about plausible sounding explanations, because it's easy to kind of go along with positive claims that sound reasonable to you. Is what I just said reasonable or not? Like, that can depend on all manner of factors. Maybe income per capita is super important, because otherwise these individuals would have to pay for vaccinations themselves. Maybe it's not relevant because all of the vaccinations are going to be provided by an international collaborative body like the United Nations. Anyways, plausible explanations aren't necessarily correct explanations. And drawing a quick conclusion intuitively from a graph like this might not necessarily always give you the correct decision to make. So just wrapping things up a little bit, every chart you see, like every visualization you see, it's sort of a claim. So if I show things this way, then people will correctly be able to answer this question. That's an important thing to get right. You could evaluate this. So we don't tend to see this too much in AI, but sometimes we do when we're dealing with explainable AI, for example. Those who do human-computer interactions in computer science tend to try to answer this question a lot more in this way, which is to recruit some people to look at the visualizations and answer specific questions given the visualization. And you measure, how often they were correct in terms of their interpretation, how long did it take them to come to the correct interpretation. Maybe you want them to be very quick. Sometimes you want them to take a bit more time to really consider the answer to the question. So you measure like how long it takes them to answer questions. If they did struggle, so if they made incorrect interpretations of the graph, or it took them a long time to come to the correct interpretation, that's when you might do some experimentation. You might do some A/B testing. You might do some ablations. So that means you might try different chart types. You might try different encodings. You might try to clarify labels or guides or other kinds of information, meta information about the graph. So a visualization that we've been looking at before is an artifact that you can do science on, and you can have a hypothesis related to information conveyance, and you can test that hypothesis through experimentation by evaluating with humans. Ethics, I'm going to lean into this a bit more again, not to sound like a broken record, but into the next module. Visualization, and I think a lot of people think of it as more of just like a acute exercise or something that has more to do, again, with form or kind of high-level aesthetics than it does to do with function or meaning. And that's the wrong way to think about it. It's not just some like afterthought that you would do to just fill up space in a report or to use some colorful thing to dazzle your reader with something pleasant to look at. The point of a visualization is to convey information properly and not convey incorrect information. So that being said, it's all about relations to the truth, and therefore it's strongly related to ethics. So almost everything we're talking about in data science has a different perspective on ethics. And in this case, indeed, if we're aggregating information out to do a visualization, this can hide important differences. Merely looking at overall income or indeed even median age in countries or mean age in countries can kind of squash useful information down into a single number that by itself might not be that meaningful. Charts that are heavily location heavy, so maps, kind of detailed scatters. This is a different angle in ethics. It can sometimes accidentally reveal individuals. I'm going to show you an example of this in a second. And then design choices. So what you decide to highlight. If you limit axes, if you change colors to draw the eye in certain areas, this can affect, who is heard, like in the data. Like if the data represents people, you can downplay certain groups or certain kinds of findings by darkening or lightening certain areas of a graph. We'll see lots of ways that things can go wrong in the next slide, or the next module. So this is all ethical related, right? So if someone took this chart seriously and wanted to take in action based on it, are they going to make a good decision? Who's going to be helped and who's going to be harmed? Like, again, we're going to come back to stakeholders soon enough, but if someone's trying to convince you of something through a visualization, like what is their goal, right? And it's always helpful to think about that when you're looking at visualizations. Otherwise, you could be easily led astray. Here's a little example of this instance of accidentally revealing people, that is to say, breaking privacy. So this is an actual study. So Strava makes this app that basically monitors your you're jogging or you're cycling. And they had this global activity heat map they released in 2018, which is 3 trillion GPS data points from runners and, more importantly, cyclists, intended as like a feature, some kind of way to interact with the community. And so the problem is that the heat map actually unintended exposed sensitive military locations. So there's links here to the BBC and the Guardian that describes this. What this means is this. So imagine somebody works at the Navy down on the Halifax Harbor. They put on their watch in the morning, and maybe they drive to work, maybe they jog to work, or maybe they cycle to work. So they're recording information about where they are at any given time, and that's all you have on them. So you have a little dots for where people are in time. You don't have their name, their age, their occupation, their gender, their sex, or anything of that nature. So like it appears to be that you're not really conveying any personal information. But obviously, in that case I just mentioned before, if you see that a particular chain of GPS coordinates spends most of their time in the base and the Halifax Harbor, and then at the end of the day, at around 5 o'clock or wherever they leave work, they happen to go to this neighborhood in Bedford or Halifax or whatever, then you could kind of obviously see that, okay, as someone who works with the Navy, who lives in this address, if I'm a nefarious government, then I can try to target that person and try to flip them to be a spy for me for some nefarious, ethically incorrect perspective or utility. So the lesson here is that aggregate information, it doesn't necessarily mean anonymous, especially if it's context-sensitive data. And when individual identities are hidden, patterns can still endanger groups like workers in our defense industry, aid workers, and so on. There's another set of projects we did looking at how certain bad actors online, helped move impressionable people to harass healthcare workers during the COVID pandemic. The same principle applies. I say principle, obviously that wasn't a principled in an ethical sense, but a principle in terms of the overall modus operandi. Summarizing, visualizations are built from visual variables, and they're organized in using this sort of grammar. And we talked about different ways that these grammars sort of exhibit themselves. When we're going about making visualizations, we have to start from the task. So, are they comparing things? Are they looking for a trend? Are they trying to identify distributions, relationships, other kinds of very low-level interpretations? Given that task, then we can go ahead and choose the chart type. For very precise comparisons, often we're going to prefer positions and lengths, which is why we tend to do lots of scatter points, because we're dealing with very small measurable distances on some continuous variable. We often have to deal with labels also, so we might use a marks color to represent things like its nominal category. So marks, channels, scales, these are the kind of, I say vocabulary, I'd characterize this more as the grammar that we use to design and even evaluate and criticize charts. Again, it's important to not just take a chart at face value and say this is a visualization and be incredibly naive about it. Like, there's different ways that we can convey information, and we want to be critical and not just accept everything we're seeing. So now we have a little bit of some tools at our disposal that we can use to evaluate whether a visualization is correct or not. And I've even highlighted a couple of instances where visualizations are incorrect. Just like everything else, visualization, you can treat it as a testable hypothesis. So will somebody get the right information from this? Will they get the wrong information from this? We can evaluate this. We can actually do experiments on humans to test whether or not they do or do not get the right information. And we can approach this as a scientific problem, not merely as a aesthetic or as a style-based one. Some very quick questions for you to answer. And thank you so much. See you next time.